Vector and parametric equations of a line in two-dimensional space, in R squared, however you want to call it. It's a new word, parametric equations. It's just an equation that has a parameter, but we're going to represent lines not in y equals mx plus b or whatever form, standard form. It's going to be using vectors. So I'll try my best to kind of have us visualize what that means. Let's take a look at the first, not example, but representation of a line using vectors. So if a line passes through point 4, 3, so I'm just going to draw a little diagram here. Let's go like this and like this. This is x, this is y. So 4, 3 is here somewhere. All right, so this is point 4, 3. And it has a directional vector of -7, 1. So this directional vector comes from the origin and goes right here, right? So this is the directional vector going to point -7 and 1. So this is point -7 and 1. And this is the directional vector. That's what that means. This is not a vector, that's just a point. Well, if I know it has this directional vector and it has to go through this point, it just has to be a line parallel to this line. So I could just use the slope of this line to represent this line and go up 1 over 7, up 1 over 7. As long as these two lines are parallel, this is me representing this scenario using a vector, right? I have a point, I have a directional vector, and I'm applying it to create this line. So this green line is the line that the question is really asking for. Okay, let's move on and think of, a line passing through 2 points. How are we supposed to set that up as a vector? Well, a line passes through the points A and B, and we want to determine a direction vector for this line and write it using integer components, so no fractions, right? We want integers here. So let's actually come up with a directional vector first. So I'm going to say, well, direction, if I can spell direction properly, vector AB, right? Because these are just 2 points. I need some sort of vector. Just like I had here, I had M. So just find a vector, AB, BA, whatever it is. And I'm going to have to use that. So AB, this is going to be equal to just the subtraction of these two. So 3 over 4 minus 1 over 2 is 1 over 4. 1 over 2 minus -3 is plus 3. So that's going to be 7 over 2. So this is my vector AB. Okay. Now I want to multiply by 4 to get it into integers. So I'm just going to, I don't know how I'm going to write this, but I want to multiply it by 4. So this is just t of 1/14. 1 over 4 times 4 is 1. 7 over 2 times 4 is 14. And I just removed the t because this is just a parameter based on this 1/14. It's the same thing. It's going to in the same direction, right? It's just stopping early when it's smaller numbers. And I pull out that, scalar, because there's an infinite number of points on that directional vector that can, tell us the slope of the line, right? So it doesn't really matter. And this is pretty much it, but I'm actually going to go on and show you what we're really doing when we're using vectors. This is kind of separate, but it's okay. So let's say I have a vector, a directional vector, M, right? So I have directional vector M, and this tells me my slope, right? So this is M, and it's a vector, AB. But really what I want to do is I want to find the equation of a line that is parallel to M. So let's say if I can draw parallel-ish right there. I want to find this equation. What's the equation of purple? Well, if I know 2 points on the line, so this is going to be one of the points, and I can call that point PO, and that's going to be XO, YO, whatever the point, it doesn't really matter what the point is. And it has to go through another point, right? So that other point can be this guy. And that's another point, P, X, Y. Really what I'm trying to find is an equation using vectors that go between those 2 points. So I can use my knowledge of vectors from the origin to these points, just like this, and like this. And that right there is going to be an addition of 2 vectors. So let's say this one is, the resultant vector of those 2 being added. Let's put an arrow here because I'm going in this direction. And we're going to call this one actually R0. Sorry, it's kind of like hard to see. And we can call this guy T in the direction of M. That's the parameter, right? It doesn't really matter. It's the same slope as M, it just has a parameter in front of it. So by triangle addition, I'm gonna write that down here in I don't know what color. So by triangle addition, I know that vector R, the resultant vector, is just the addition of these two guys. So this is just gonna be R naught plus T vector M. Okay, and this right here, this is a vector equation to represent that line, that purple line. I'm using two vectors to represent. I can rearrange this formula, right? I can subtract these two green vectors to get the equation of the line. It doesn't really matter, but this is a vector equation. Okay, now parametric equations isolate the x and the y. So I'm just going to erase this here for a second, continue with the same screen. Parametric equations separate the x and the y. So what's that mean? It means that I just want to know what the x value is and what the y value is. So I actually separate them. So for instance, if I have these guys as my parameters, sorry for the overlap there, I want to know that x is x naught plus ta and y is y naught plus tb. Okay, so what's this mean? This means that I'm just isolating the x values and coming up with a parameter for x. Okay, and these are called, when I separate x, y, and z, these are parametric equations. Right, and once we have z too, we're gonna include another parametric equation for z. Okay, and it's a parametric equation because this right here, this t, this is a parameter. Right, that could be any real number, really, whatever I did it in that previous example that was here that I erased, but that's pretty much it. So we have to be able to use vector equations and parametric equations versatilely, that's a word I just made up, in order to solve problems once we start applying, vectors. Okay, so for example, we want to come up with the vector and parametric equations of a line passing through this point with this directional vector. So I just listed the vector equation and the parametric equations here. So we're going to do both over here. Okay, so all we really have to do to come up with my chicken's ready. All we have to do to come up with a equation for that vector is say, let's use purple. Well, I know that vector r must be equal to the point. So you always list the point, right? Because you need a point in space to start directing this vector, because all of our vectors come from the origin, right? We don't want that because the line could be anywhere. And I'm going to add some variant of my direction. And this is it. This is the vector equation for that line. That's all there is to it right now. Obviously this question is easy because it gives us this information. It gives me the vector m, it gives me a. But this is all that's required for coming up with a vector equation. You want to come up with a parametric equation? No problem. Stay in the same color. X equals 1 plus negative 3t, or minus 3t, however you want to say it. Y equals 4 plus 3t. So here we have our vector equations, here we have our parametric equations. Okay, there is something you can note here, is that I can actually factor out a 3 from this point, because if the directional vector goes through negative 3, 3, it goes through negative 1, 1, right? So why use larger numbers if I don't have to, if I'm still multiplying them by some sort of parameter, right? I'd rather multiply a negative 1 and a 1 by that same parameter. So this is actually the exact same equation, but better. Right, because that t value could be a 3. Doesn't really matter. This is much easier to work with. And it's the exact same line because we're going through that point and we have the directional vector of negative 1 and 1, which is the same as that direction. Okay, and if I want to come up with the new parametric equations, I can say x equals 1 plus negative t, or 1 minus t. You know what? I'm going to do that. That's disgusting. All right. Or we'll call it differently now because to come up with a different variable. It doesn't matter what variable you're sticking in front of there. But y is 4 plus s. So these are better parametric equations because the numbers are smaller. That's pretty much it. Okay, these lines are identical. Okay, the second one is just more simple. The blue one is simpler. And if I want to find any other points on this line, all I have to do is plug in parameters into here. So I want to find a point on this line, I can plug in 0 over here and have the xy. If I want to find another point, I can plug in 1,000,000 over here and I have an xy component, another point on that line. Okay, I can do that here, I can do that here, it's going to be the same thing. All right. Okay, and the final two questions here, we're going to do a similar one that we just did, just to kind of solidify. Then we're going to apply different concepts that we've done in grade 9, grade 10, just to see how we can work with, you know, these different forms of lines. We understand lines, but this is a different form of a line, so how can we work with it to kind of solve problems? So we want to determine a vector and parametric equations for the line containing these 2 points. Again, you need a directional vector from one point to the other, and you need a point. That's it. There's nothing else to it. So our first directional vector, or our only directional vector, which is m, can be in the form of vector EF, because those are the 2 points I have. So vector EF is just 7, 6, right? Really easy to find. 6 minus negative 1, 11 minus 5. Now, that's it. Therefore, my equation is R, vector R is pick a point. I'm going to pick this one because I'm staring at it. That's the only reason. And that's going to be plus the parameter plus the direction. Sorry, the direction included on there. Here's my vector equation. Done. I want my parametric equations, break them up. X equals negative 1 plus 7t, and y is 5 plus 6t. Now, how do we use these things? Well, if I wanted to find the x or y intercept, if I wanted to find the x-intercept, I can set y equal to 0, solve for t, and that's going to tell me at what parameter that y-intercept is going to occur. So if I want to find the x-intercept, if I find that parameter, I can plug it into t over here, and I'll find the x-intercept. Okay, and vice versa for y. So I can use these kind of same way I've always used x, y coordinates. There's just a parameter there that we have to solve for. Okay, so this next equation or question is a little trickier. And that's only because we haven't seen it before, right? It's pretty straightforward. We want to determine a vector equation for the line that's perpendicular to this directional vector r, okay, plus this, this is the whole vector, and passes through this point. Okay, so we have a line, but it's got to go through this point and it has to be perpendicular to this line. So how do we do that? How do we understand that? Well, the directional vector here, m, is this negative 3, 2, right? So it's really important because if I have a directional vector, I need that perpendicular directional vector. So how do I find a perpendicular vector? Well, if I know that v is going to be perpendicular to m, right? I'm just coming up with v. I've got to find some sort of vector. I know that then m dot v must be equal to 0. So here we bring back dot product again to figure this out. You don't have to do this every single time. I'll show you a quick hack on how we can find perpendicular things, you know, like negative reciprocal, whatever that, you know, translates to in vectors. But this just means that negative 3, 2 dot some sort of other values must be equal to 0. Negative 3a plus 2b is equal to 0. So from here, I know you're thinking, oh, but there's 2 variables, how are we supposed to solve? But I mean, really, it's equal to 0. So if I plug in a 2 here, I get negative 6. If I plug in a 3 here, I get positive 6. So I can just switch these coefficients, and I'm always going to get 0 as long as the sign's opposite, right? So here I understand that a is equal to 2 and b is equal to 3. Okay, and that's it. Now I can finalize my equation that r is equal to 6, 5. We always start with that point, right? And we add the directional vector with some sort of parameter in front. And this is it. This is our answer. Okay, now, do we always have to do this? Absolutely not. We do not have to do that all the time. All you have to do to find a perpendicular direction is flip your numbers and negate one of them. And that's what we did. From -3 to 2, we changed it into 2, 3. We could have also done -2, -3, right? But why would I want to put two negatives if I can not put two negatives? So both would be correct. So again, you want to find a perpendicular slope to a vector, you flip the numbers and negate one of them. Done forever. And that is 8.1.